Welcome everyone. Today I'll introduce Bindex, a compact, structured knowledge layer that helps AI agents understand and correctly use software libraries. The core idea is simple: AI does not need to read an entire codebase every time it wants to use a library. What it needs is the right context, what the library does, how its APIs should be used, what constraints apply, and what examples it can follow. A good way to think about project context is as an iceberg. At the visible tip, we have APIs. They show what can be called, but not always how, when, or why to use each capability. At the waterline, we have documentation. It can contain valuable explanations, but it is often scattered, verbose, or outdated. And deep below the surface, we have source code. That is the ground truth, but it is too large and too expensive for AI to repeatedly analyze in full. Bindex exists to transform this hidden and scattered context into a compact AI-readable contract. In a truly large-scale enterprise, the problem is multiplied. We aren't just dealing with one codebase, one iceberg. We are looking at an entire horizon of icebergs. Our enterprise ecosystems consist of dozens of independent libraries, utility modules, and artifacts scattered across different, isolated repositories. Modularity is great for humans, but a nightmare for AI. The actual business logic, the tricky edge cases, and the architecture of these libraries are buried deep inside the source code. But when a developer or an AI wants to use an existing library, they shouldn't have to perform deep code surgery just to understand how to call it. To make this high-level understanding possible, we must leverage something we already have: standard in-code documentation. I'm talking about JavaDocs in Java, docstrings in Python, and tsdoc in TypeScript. For decades, developers have left important context inside the code. Comments explain why something exists, how it should be used, what assumptions it relies on, and what traps to avoid. Historically, these comments were mainly written for other developers. However, there is a catch: outdated comments are a silent killer. If a comment is wrong, the AI will trust it blindly and generate broken code. In the AI era, a lying comment is infinitely worse than no comment at all. This makes keeping our documentation accurate and up-to-date an absolute operational priority. Writing code comments for an AI requires a completely different approach than writing for a human colleague. When humans read documentation, we rely on intuition. We can read between the lines, tolerate conversational fluff, infer missing types, and cross-reference messy, external wikis when we get stuck. AI agents, on the other hand, cannot read between the lines. They require structured, literal, and self-contained context. For an AI, there is no common sense to fill in the blanks. If an input constraint, dependency, or copy-pastable code example isn't explicitly defined in the structured comment block, the AI simply cannot guess it. We must shift from conversational writing to structured metadata design. This is why the role of comments changes in the AI era. They are no longer just helpful notes for human developers. They become the AI's map of the library. If comments are structured, explicit, and close to the public API, they give the AI a reliable way to understand how the library should be used. Instead of reverse engineering intent from raw implementation details, the AI can follow verified in-code context: what the API does, what inputs it expects, what constraints apply, and which usage patterns are recommended. So developer comments become more than documentation. They become part of the AI infrastructure around the codebase. Of course, maintaining this manually is a daunting task. The solution is to close the loop. We use AI to help developers draft and update these in-code comments as they write code. Crucially, these comments must be verified by the developer before the code is committed and released, ensuring they remain the ground truth. Once these structured comments cover all public integration points, we can automatically compile them into a standardized, clean API reference that perfectly reflects the library's capabilities. Documentation still matters. A lot of important context does not belong directly inside method-level API comments. For example, architecture notes can explain the design intent. Setup guides can explain how the library is initialized. Tutorials can show common workflows. Business rules can explain why certain behaviors exist. The problem is that this information is usually scattered across many places: wikis, portals, repositories, project documents, and release notes. For humans, this is annoying but manageable. We can search, ask questions, and interpret context. For AI, this fragmentation becomes a serious problem. If we feed everything into the model, we create noise. If we feed too little, the model misses important meaning. So Bindex does not try to consume all documentation blindly. It filters the valuable parts and connects them to the actual API. Bindex is built from two main kinds of input. The first is API structure. This is the technical skeleton of the library: signatures, types, parameters, return values, constructors, constants, public classes, and extension points. The second is filtered project context. This includes the high-value parts of documentation, functional guides, business rules, architecture notes, usage examples, constraints, and integration patterns. Together, these inputs provide both sides of the picture. The API structure tells us what technically exists. The filtered context tells us what it means and how it should be used. Bindex combines these into a form that is much easier for AI agents to consume. This is where the transformation happens. An LLM processes the structured API information together with the filtered documentation context. But the goal is not to create a generic summary. The goal is to connect meaning to specific technical elements. For example, which business capability maps to which class? Which configuration option affects which behavior? Which examples demonstrate which methods? Which constraints apply to which parameters? Which extension points should be used for customization? This creates a semantic map of the library. That map allows AI to reason from intent to implementation. So instead of asking, what methods are available, the AI can ask, what capability do I need, and how should I use it correctly? You can think of Bindex as a compiler for library context. Instead of compiling source code into executable artifacts, Bindex compiles verified library knowledge into an AI-ready manifest. The pipeline has 4 stages. First, it analyzes the API structure, verified comments, and selected project context. Second, it connects that meaning to the relevant packages, classes, methods, constructors, features, and extension points. Third, it structures the result using a standardized schema. Finally, it emits a compact file, bindex.json. Under this model, the codebase remains the source of truth. If a detail is important for correct integration, it should be captured in verified code-adjacent context. Otherwise, we should not expect the AI to use it reliably. The output, bindex.json, becomes the AI's compact map to the library. To make Bindex usable across many libraries, every bindex.json follows a consistent schema. Some fields describe identity, ID, name, version, authorship, license, and location. Some fields support discovery, description, and classification, help AI understand what kind of library this is and when it might be relevant. But the most powerful fields are the integration fields. Features describe the main capabilities of the library. Constructors explain how objects or services should be initialized. Customizations describe configuration and extension options. And studs describe gateway contracts. In clean architecture terms, these are gateways, interfaces, or abstract types that define how external modules, adapters, or implementations plug into the library boundary. Finally, examples give the AI concrete usage patterns to follow. So the schema does not just say what the library is. It tells AI how to use it, configure it, and extend it safely. This UML diagram shows the exact anatomy of a Bindex brick. Just like Lego blocks, our libraries are designed to snap together perfectly. The bindex.json manifest answers 3 critical questions for developers and AI agents. What is this library? Where does it live? And how do I execute it? By removing the guesswork, we allow AI to assemble working integrations instantly and safely. Let's zoom in on the yellow block in our diagram, classification. This is the brain of our discovery system. When a developer or AI searches for a library, we don't just match keywords in file names. The classification block defines the domain, target environments, architectural layer, and supported programming languages. This rich metadata powers high-precision semantic search. Next, look at the highlighted attribute, the description. This field powers the second stage of our engine. After semantic search narrows down the candidate libraries, the AI analyzes this deep, contextual description to ensure the library is a perfect situational match before recommending it. As you can see, this schema bridges the gap between high-level business requirements and low-level code compilation. By standardizing this schema across our entire ecosystem, we create a unified, common language for both humans and machines. The final value of Bindex is that it gives AI one compact starting point instead of forcing it to inspect an entire codebase. Each library gets a lightweight AI-ready contract. That contract can support semantic search, the AI can match a business need to the right library based on descriptions, classifications, features, and examples. It can support integration. The AI can understand how to initialize the library, which APIs to use, and what constraints apply. And it can support safe composition, gateway contracts, or studs, tell the AI where other modules are supposed to plug in. This creates a shared language between humans, libraries, and AI agents. Instead of scattered docs, raw code, and disconnected APIs, we get a compact structured manifest, bindex.json. That is the purpose of Bindex, to make libraries discoverable, understandable, and usable by AI. Each one of these has its own hidden depths. To make AI work across our entire project, we can't just index one module. We have to deploy our Bindex pipeline across every single library on this horizon. By deploying these standardized contracts everywhere, we turn what was once a disconnected archipelago of isolated codebases into a single, cohesive, AI-navigable playground. No matter how deep or complex the code lies underwater, Bindex places a visible, standardized flag on top of every iceberg. The AI no longer has to guess what lies beneath the surface. It can scan the entire horizon, read the flags, and immediately understand the boundaries and capabilities of our systems. This is how we search. Instead of a developer spending hours hunting through dusty repositories and outdated wikis, the AI reads the Bindex catalog to instantly locate, verify, and pull the exact brick it needs. In conclusion, Bindex gives both AI and developers laser-focused vision across the entire enterprise. It turns code discovery and integration from a chaotic bottleneck into an effortless, structured superpower. Until now, we talked about Bindex as a concept, a compact semantic contract for software libraries. But Bindex is not only a schema or a JSON file. It is also supported by a practical toolchain. The main component is Bindex Core. This is the library-level engine. It is responsible for working with Bindex metadata, reading it, validating it, and making it usable by other parts of the system. If bindex.json is the contract, then Bindex Core is the component that understands that contract. The Bindex Core documentation is available at machai.machanism.org/bindex-core. There are many ways to use Bindex, but in this demo we will use a lightweight assembled version that includes only the Bindex Core functional tools. We will focus specifically on the Bindex-related MCP tools, not the full Machai toolchain. The project repository is available on GitHub under MachanismOrg/Bindex MCP Server. For the demo, we will use the release package from this page to run the server locally. Before we start using the Bindex MCP tools, we need to prepare the local Bindex repository. In our case, we will use a repository available inside the local network. This repository acts as the local catalog for Bindex metadata. It stores registered bindex.json records and makes them available for discovery, lookup, and library recommendation. The Bindex MCP server will use this repository when Claude asks it to register a Bindex file, retrieve metadata by ID, or pick libraries based on project requirements. The setup details are described in the Bindex Core local repository documentation. Next, we configure the Bindex MCP server. For this demo, we use an mcp.properties file, but the same settings can be provided in different ways: environment variables, system properties, properties files, or a combination of them. The Bindex settings define how the server connects to the local Bindex repository. Here, the repository URL points to a MongoDB instance in the local network. The GenAI settings provide access to the GenAI provider. The gw.model setting defines the main model used by the toolchain, and embedding.model defines the model used for semantic search. In a real setup, credentials should be stored securely and not hard-coded in shared files. To make the first test simple, we can use Claude Desktop to run the Bindex MCP server locally. In this configuration, Claude registers a new MCP server named Bindex and starts it as a Java process. The jar argument points to the packaged Bindex MCP server file. The C argument points to mcp.properties, where the server configuration is defined. The D argument defines which part of the local file system the MCP server is allowed to access. In this example, D // gives access starting from the root of the Windows file system. This is useful for testing, but we should be careful with it, because the MCP server will be able to access files under that allowed directory. For a safer setup, we can point D to a specific workspace or project folder instead of the full root directory. Once this is configured, Claude can call Bindex tools through MCP and use the allowed local file system scope for discovery. Once Claude connects to the Bindex MCP server, it gains access to 4 main tools. Get Bindex retrieves structured metadata for a specific library. Pick libraries helps Claude find libraries that match a project need. Register Bindex adds an existing bindex.json file from a local path or URL. Register bindex.json registers existing Bindex metadata directly from JSON content. The important limitation is that this MCP server does not generate bindex.json. Generation is a separate pipeline, and that process will be covered in the next video. Now we register an existing bindex.json file in the Bindex MCP server. In this example, we provide the local path to the bindex.json file from one of our project libraries. Because the MCP server was started with local file system access, it can read this file directly from the allowed directory. Here, we ask Claude to call the Bindex registration tool directly. We are registering an existing Bindex file so it becomes available for discovery and later retrieval through MCP tools. The tool returns Bindex ID identifies the registered library. This ID becomes the stable reference that Claude can use later to retrieve the library metadata with Get Bindex. We're using the local Bindex storage. Let's open it and take a look. Each registered library becomes a document in the Bindex collection. The saved record contains the original Bindex metadata, as well as searchable fields such as name, version, description, domains, and layers. After registration, Claude can search this catalog, select relevant libraries, and retrieve full metadata by Bindex ID. After registration, we can use the generated Bindex ID to retrieve the metadata again. Here we ask Claude to get the Bindex record by Bindex ID. Claude does not need to know the original file path anymore. It can call the Get Bindex tool with this ID, and the MCP server will look up the registered metadata in the local Bindex catalog. This is the main difference after registration. The library becomes addressable by a stable identifier, not by a local JSON file location. After Claude retrieves the Bindex record, it can use the metadata to explain how the library should be used. It identifies the Maven dependency, required repository, key classes, dependencies, and common usage patterns. Then it provides practical examples for different configuration sources and shows how the library can be extended. The main point is that Claude generates useful integration guidance from Bindex metadata, without reading the full source code. Now we use the Pick Libraries tool. Instead of asking for a specific Bindex ID, we describe what we need in natural language. In this example, the requirement is configuration support for a Java application. Claude sends this request to the Bindex MCP server, and the server searches the registered Bindex catalog for matching libraries. This demonstrates the discovery use case. The developer does not need to know the exact artifact name in advance. The MCP server returns a recommended library from the registered Bindex catalog. In this case, it selects the configurator artifact as the best match for configuration support in a Java application. The response includes a relevance score, a short explanation of why the library fits, and the main capabilities it provides. It also highlights key classes, so the developer can immediately understand which API surface is important. This is the discovery value of Bindex. Claude can move from a natural language requirement to a concrete reusable library. Bindex turns hidden library knowledge into structured AI-ready context. Instead of forcing an AI agent to inspect raw source code or scattered documentation, we give it a compact semantic map through bindex.json. With the MCP server, that map becomes available directly to tools like Claude Desktop. The AI can register Bindex records, retrieve metadata, and pick matching libraries based on natural language requirements. The bigger vision is simple: every reusable library should expose a trusted AI-readable contract. That is how we make software libraries discoverable, understandable, and reusable in the AI era. In the next video, we'll look at how bindex.json files are generated and how the Bindex creation pipeline works. Thanks, and see you in the next video.